we talk about continuous symmetry, do you mean different type of operators which commute?
No, the simplest case, in this lecture, I only had one operator running on a circle. So everything is by definition commuting because it's constructed from one matrix. So any function of the matrix is still commuting. When we did this for discrete groups, we did discrete groups in two steps. One is we ran on a discrete circle on a ring of, that's a billion group. It was easy to do. Then I had to teach you just one non-abelian example, which was look at the triangle and flip it around, or three disks. And if you understood that, you basically understand everything you need to know about discrete groups. So I'm repeating the same logic this week. Today, I'm running on SO2. That's just the limit of a cyclic group, but now it has infinitely many elements because I can do it in arbitrarily small steps. And, the main lesson is that you have to look at the generators, things in exponent, rather than group elements. There is only one generator, but there are infinitely many group elements. So that's the main thing which you always have between discrete and continuous. For continuous, we have to look at differentials or generators or something. Now, on the rest of this week and whole next week, I will only do, the triangle. The first non-abelian example, it's called SU2 if it's on complex numbers, or it's called SO3 if it's in our space. And that's all you need to learn conceptually to understand. When you have non-abelian groups, you have to, for finite groups as opposed to cyclic group or Fourier analysis, I had to learn multiplication table to define the finite group. The multiplication table for continuous group will be called Lie algebra. I'll have to figure out if I combine pairs of generators as a commutators, in two different orders. I'll have to find a multiplication table for that, whatever, some kind of constants of the group. But it generates, and once you understand it for a rotation, you understand it also for all particle physics, for all SUNs and everything that happens in particle physics of standard model. And for condensed matter physics, where you have more interesting symmetries than just a rotation in three-dimensional space. Now, for me, the amazing thing that we learned in the process is that our space is built from complex two-dimensional blocks and not three-dimensional bricks. That's totally amazing. And it has to do with the Nobel Prize in physics this year, because, I'll go back to Roger Penrose. Totally unexpectedly, they gave a prize to somebody who deserves it. Because by any rule of the game, this guy should not get a prize because he is smart, he is creative, he is inventive, and, he doesn't play the game. He's always doing something screwy. So he shouldn't get a prize. But actually, the way he got started as a graduate student, he was trying to build space-time for spin 1/2 particles. And that is the story that involves also Georgia Tech in an interesting way. But, being smart and creative, he decided to drop that and do general relativity. Then he dropped that and he did tiling, and then he dropped that. And he decided that because brain is complicated, quantum mechanics is complicated, it must be that, consciousness is a quantum phenomenon. So all the neuroscientists are totally pissed off at him. Then, he did something else, cosmology, this and that, just a bunch of crazy ideas. He's so smart. This book that I, keep trying to tell you, get it and read it. It's totally amazing. And it's, supposed to be a child's course, like I'm teaching you children versus mathematical methods. He's teaching you children's version of everything, and you can only understand it if you are a theoretical physicist with 30 years experience. But it's supposed to be for everybody. Anyway, so the short answer is no, we do not assume in general that these operations commute. It's totally essential they don't commute. But we do assume they're closed. So operation of few of them has the group property that the result is also a group element. So we have closure. That's totally essential.
You touched about the consciousness and the mind being quantized, being quantum mechanics. Do you believe that the brain is some kind of is something that we will be able to understand in the future using physics and quantum mechanics, or are you saying there's something beyond that?
Well, in our current understanding this only requires classical physics and non-quantum chemistry, and it's unlikely. I mean, just on the scales and on what we know, it's mechanism. Like you don't need, strictly speaking, quantum mechanics to understand how the car works. Unless you really try to go to the atomic level of combustion, etc. At some point you encounter quantum mechanics, but not in a way we want to get a description of brain. The consciousness is another thing that it's more subjective, but the brain itself is doable. Yes, we will have a rather detailed understanding of human brains. And it won't be pretty because the fascists will use it. The fascists will be with us. So, but yes, it's inevitable. It's very painful. I have a friend who is a graduate student in neuroscience. Already 7th year, he suffers terribly because, the work is incredibly boring and difficult and unrewarding on the local level, but on a global level, we will understand, mechanics of cognition much better. And we do this, every year is significantly better than the previous. It's within reach. And, there's always a hope. I don't know about where that will work out. There's always a hope that there will be Newton laws of of cognition, and maybe yes, maybe not. Newton laws, in retrospect, are incredibly simple things. Celestial mechanics is incredibly simple compared to many of the things you studied today. So I don't know where those laws will be framed, but the understanding definitely will increase, and with it will come the power to manipulate, to control, and to change the direction, etc. All of those things will happen.
Even because
it will be your problem, not mine.
Might as well.
Because it won't happen tomorrow.
Yeah. So you're saying the electron and the electric current in the brain could be explained classically? Wouldn't be required any quantum interpretation?
Yeah, I mean, it's really, the way it works is you describe the concentrations of ions, none of this seems to require quantum mechanics. For example, we had a beautiful colloquium by Julia Yeoman yesterday, and she showed the picture of E. coli motor, and we can't really see it, but it's motor, and it's only on the level of burning the ATP energy that quantum mechanics is the mechanism that how it does. And even I'm not sure there, lots of chemistry doesn't require quantum mechanics. But beyond that, these are just concentrations of ions, going through membranes, not going, everything seems to lend itself to classical ways of thinking. Phenomenological, but everything we do is phenomenological on the level that we do. we define it as phenomenological.
Were you saying about The Road to Reality by Roger Penrose?
Yeah.
Over 1,000 book pages. Okay.
What about it?
No, I was actually able to obtain an electronic copy of it, but I was
Well, you
wondering,
just click. What do you mean you're able? If you click
I mean, I
and you
was,
remember the password, I have one stored for us in the Chaos book, internal library. But yeah, you can obtain it electronically anywhere you want. Yes. The beautiful thing is, a very good doorstop. I mean, it's like that. I have the physical one. And I read the physical one, it's more pleasure. He likes to draw by hand, so the illustrations, you smell the paper, you turn, and there is a hand-drawn thing, It doesn't feel like a machine created this book. So,
when we talk about symmetry, are all the laws of physics are time invariant beside
that's actually, that's a profound question. So Andrei Sakharov, who got Nobel Prize for Peace, was one of the parents of hydrogen bomb, the Soviet version as opposed to American version. As a physicist, he was very interested into the idea that as the universe evolves, the fundamental parameters, in particular fine structure constant of electrodynamics, changes on the universe evolution scales. Now that's a big deal because all of our chemistry and everything, water, everything that we have depends on fine structure being what it is. If it's changed, the chemistry changes, everything changes. So we do not know. I mean, all we know is that if we assume that for 13 billion years, the electrodynamics or our laws are immutable as the laws, we get present cosmology, and it's somewhat consistent except for the dark energy. But as far as we know, we have not measured. People try to do this in atomic physics where they have very precise measurement. We have not measured any drift of parameters of laws of nature. Now, if the laws change not just in terms of parametrization, but qualitatively, suddenly they get other interaction terms or lose them, that would be even more amazing. So far, we haven't noticed these things. We have never noticed significant violations of Minkowski invariance. That would change the special relativity. That would change everything. We haven't been able to measure change in gravitational constant or in fine structure constants, which are two that we can measure rather precisely.
What about the
especially fine structure constant? We have it to 13 digits, and we haven't noticed any drifts any place. So on our scale, our perception of universe, but this now we're talking billions of years, they're immutable. Now, if you prove otherwise, more power to you, we will all follow you.
I was wanted to ask about the expansion of the universe. If you think there are any indication, obviously it's accelerating, but do you think there is any indication that it's going to slow down or maybe reverse in the future, similar to what Stephen Hawking was?
I don't. I mean, I'm totally reactionary, so I don't believe anything or anybody that I don't understand. So cosmology is always the most suspect of all of physics. Because by nature, we have only one experiment which we're aware of, which is, this particular universe. So it's very hard for us to play games and test the ideas. But in terms of observational evidence, the astrophysics in the last 3 decades have changed orders of magnitudes, made it orders of magnitude more respectable. Still, I would be very happy if we got rid of inflation, if it turned out that there was no dark energy things. We misinterpreted some measurements or did something. For me, it's open for the professionals. I'm being offensive, and they would be, beat me up in the dark hour that I say this. But I'm kind of hoping that some of that stuff will go away, because it's profoundly unsatisfactory, intellectually, some of these things.
Obviously.
It doesn't, nature might choose to work in the ways which are profoundly unappealing to myself. I mean, nature doesn't care. But we always have right to hope that things will get more sensible.
When we talk about the flow of time or the error of time, this is indicated only by the second law of thermodynamics, that entropy in a closed system has to increase.
Well, on average increase, it fluctuates.
Yeah.
So there are violations of the second law on sufficiently short time scales, and they're theoretically solid and they're experimentally measured in some cases within last 10, 20 years. And if you learned chaos theory, you discover that even having just few particles, you don't need the Avogadro number of them, you get an error of time whenever you have an exponential loss of information in a time flow. So it's not so mysterious like it was for Boltzmann, Maxwell, people who created this theory. But, again, I might be wrong. I mean, but, empirically, that's how it works for us. Let's say I sleep very peacefully when I think of error of time. I just turn over and fall asleep again. Nothing, no suicidal thoughts about that.